Okay, my friends, it looks like we are there. If nothing else, while people are walking in, let me get some housekeeping out of the way. My name is Cliff Cummings. I'm the VP of Training at Paradigm Works and founder of Sunburst Design. I'll be moderating the session entitled UVM, Knobs and Sequences. We have 3 interesting papers in this session that runs until 4:30 p.m. Pacific time, and the best paper presentation starts at 5 p.m. So you have very little time to get your ratings and votes in for best paper. All of the authors, like all of the authors at DVCon, have spent a large amount of time preparing their presentations. So please quickly take time to cast your votes at the end of each paper. And I'll try to remind you again to vote at the end of each paper. Rich Edelman will be giving the last paper presentation at DVCon, but he deserves your vote consideration just as much as any other presenter at DVCon. So please vote. Please post your questions in the chat window, and they will be addressed in the Q&A session at the end of each presentation. So let me introduce Siddharth Krishna Kumar of Samsung. Siddharth works as a staff verification engineer at Samsung Research Center in Austin, Texas. Siddharth lives in Austin and has spent almost 10 years in industry. Siddharth has worked in different domains, including networking, storage, CPU, and GPU. Siddharth focuses on reusability and scalability in most of the code he develops and loves solving problems to benefit his team and organization. Siddharth has published a paper in the past for the Synopsys Users Group and has a patent to his name. When not working, Siddharth loves to play and watch sports. So after DVCon, Siddharth is probably going to sit down in front of a TV and watch hours and hours of March Madness basketball. But for now, let's watch Siddharth's presentation entitled Advanced UVM Command Line Processor for Central Maintenance and Randomization of Control Knobs.
Hi folks, this is Siddharth Krishna Kumar here. I work as a design verification engineer at Samsung Austin Research Center in Austin, Texas. This is my presentation on the advanced UVM command line processor. Before I begin presenting, I just wanted to walk through the agenda of things we'll be discussing today. First up is a brief introduction on what is the command line processor. Next is a set of scenarios which kind of was the inspiration for me to actually develop this code. Then we'll talk about some of the nitty-gritty features of the code, followed by some coding examples. Once we have finished discussing everything about the code, I want to briefly touch upon the benefits and some of the drawbacks of the code. Finally, I'll be discussing or touching upon some of the future enhancements which have been thought about but have not been implemented yet. And the last 5 minutes is reserved for some question and answers. So let's begin. The UVM command line processor is the base class which comes with the UVM package. And this advanced command line processor is a custom extension of the UVM command line processor. This was an intentional step because I did not want 2 of these classes lying around in any code base. And at the same time, not for the user to lose ability to access all the base class methods, which are very powerful and provided by UVM command line processor. Centralized maintenance and randomization of control knobs. This is one of the keys of this advanced command line processor. Want to maintain it in a central place and have a powerful randomization around each of the control knobs. The design has been kept simple and lightweight intentionally so that it's powerful, robust, yet portable, and it's kind of like a plug and play into any UVM environment. And then one of the main intentions behind developing this code is to reduce variables in test bench code. It removes or negates the necessity to have multiple fields. It eliminates the need to have long, clunky code, which is repeated over and over again in different packets, different components, different sequences, etc. And finally, something cosmetic that want the command line argument to kind of convey what kind of traffic are we shaping instead of trying to look at the values provided in the command line arguments and then go through the code base to actually figure out how those values are handled. So let's talk through some of the scenarios which are very commonplace. We encounter them in our day-to-day activities as DV engineers and as part of any test bench code development or debug activity. Delay knobs. All of us have had the chance or the need to basically delay packets in our interfaces in a bursty fashion, sometimes not delay at all, or sometimes create longer delays, and myriad scenarios like that to basically stress our duct, especially in back pressure situations. The typical approach, which even I have followed, and which is not wrong, is basically to provide a min and a max value from the command line, and somewhere in the packet constraints create a delay which basically is between min and max randomized. So if you set the min and max to be the same, the delay is always the same value. If the min is 0, max is 100, the delay can be anywhere between 0 and 100. This has its own shortcomings, right? One thing is that you always have to provide one min value and one max value, and you're always kind of put in that one single bucket between the min and max. What if we want, say, a delay of 5
Aiden,
or
have we
less
lost audio?
most of the time, but suddenly we want a spike of 100 cycle delay? That sometimes gets a little tricky, and we have to write equivalent code to basically solve that situation. So this is one of the common situations which I've thought. The next, which is probably more specific to people in processor land and GPUs, is shaping instruction set architecture. We typically have like about 100 plus instructions, and sometimes some instructions are more stressful for certain blocks, and we want to shape our traffic in such a way that we restrict ourselves to certain opcodes. Now, not all these opcodes are consecutive, so sometimes it can be challenging to control the traffic. And all of these opcodes also are in hex values, and if you use the default UVM command line processor, you have to pass in hex values, which is kind of clunky because you now need to be mapping every opcode which you need to its equivalent hex value and then providing it in the command. It can get a bit challenging. It's not impossible, and we all have done. The next very common is instance-specific control. Set config db in command line is used to control value of fields per instance, right? You can basically, if there's a field in a particular sequence and a particular instance of sequence, you can control that by using this using this keyword in the command line, and you can provide it a certain value. But again, we are restricted in providing a single value, a single string, or a single decimal value to this field. And it becomes difficult to kind of create a randomization of that field. So now let's look at some of the actual code and the features of these code. The most critical data class is the A command line ops. This is the class which forms the data packet, which stores the values, min, max, range, and the weights, and actually for each of the control knob which we want. So this can be like as small as 1 or 2 control knobs in a very small test bench to like thousands, 2000s of control knobs in SOC kind of environment, right? So I've kind of tried to show kind of a flow of the methods as well as explaining the methods. The first method is the parse op, which accepts a string. This is kind of the magic sauce or the special format which I have enforced after talking to people and figuring out what is needed versus what looks intuitive and what is simple, right? So if you look at it, you give a command line with a bucket. For me, for advanced command line processor, a bucket is a min value, a max value, and a weight. Okay, or it could be just a single value and a weight. And you can tack it on. You can keep adding buckets and buckets to a single command. What happens next? The next step is parse val. Here, it's even more useful that this can not only accept decimal values, but it can also accept hex and binary. This is super useful. Like, why is hex useful? Hex is useful for you want to control like large hex values like 48-bit or 64-bit addresses from the command line. And you want to hit certain addresses a weighted number of times. And whereas the other addresses, you don't care about that much. Binary is also useful, especially for one-hot cases or, where you want to kind of are trying to give up or trying to give some operands where the position of the ones matter. So it's super useful. The next function method, which is part of the A command line ops class, is the set weight key. This is again how we kind of keep track of what weights was provided. Also remember, if no weight was provided, a weight of 1 is automatically added to each bucket. This queue is created by pushing in the bucket value as many times as the weight. And this is used in conjunction in the next step, which is the get random, where we create a std randomize call in conjunction with these buckets to actually get a random value. So your max or you could get a value which is provided in a command line based on the weights between a particular bucket. So first thing what happens is you first randomize and pick a bucket, and then you randomize within that bucket to a min or max. So say you, in the delays example which we were talking about earlier, you provide min of 0, max of 5, and you give it a weight of 99, and say you give comma 100 with a weight of 1. So most of the times you're going to get a packet delay less than 5. But there's this one odd chance where you would get a packet delay of 100. So that's kind of the use case over here. Okay, remember I spoke about the opcodes there, right? And how it is kind of not human readable sometimes, or it gets clunky. So the solution to that is to be able to support enums, right? So the A command line ops enum, which is an extension of the A command line ops, is used to store all these values, min, max, range, weights of the enums. And the only method which we override is the parse val. What happens is the parse val accepts a string, but at this time it knows that it is a string which is passed and not a value, not a hexadecimal or decimal value, even though you can pass that, right? And basically, once it detects a string, it will map that string using the default UVM enum wrapper method, which is like a static method, used to map string to an enum, and it is stored as a long int, right? So that's the other thing, all the return value, everything is stored as a long int because of this, and which also helps us support 64-bit values. So the A command line processor, this is the main class, which basically maintains the database of all the objects created of the type A command line ops. And it also provides the API methods which are used by the users. Most of the functions and fields are not being protected or private, so user can directly access them, but it's not advisable and it's not in the best interest to use that. And I'll show you which method the user really cares about and needs to call while everything else flows under the hood. So getInst returns the singleton handle of the class. So this is something which you will need to include in any of the common package. So if you have like a environment level package, or if you have a company-wide package, you can basically get an instant of this and then pass it around to all your test benches. Next thing is this is valid method. If you look on the right side of the screen, string, it accepts toString. So remember, the command line arguments do not replace constraints. They just enhance the ability for users to shape the traffic once over the default constraints, right? So your normal course of operation, your default constraint needs to kick in, and nothing from the command line should shape the traffic. So isValid is basically a method which the user can put to basically prevent command line overrides of any of the default constraints. And only if someone actually provides something on the command line do you need to use this method and not use the default constraints. And I'll show this in our coding examples. As I was mentioning, the main or the most super useful method which the user needs to invoke is the getRandVal. This method basically has a long list of arguments, as you can see. Each of them is described well in the paper. Please refer to the paper to know what each of these arguments are. Essentially, only the first argument is required, which is basically the string to match the name of the control knob, which the code is looking for, versus the name of the control knob provided in the command. Rest all are optional, but are super useful. This method errors out if an illegal format is seen in the command line or if no values are provided. So that is why you need to first check using the isValid before calling this, because you don't want to be calling something which the user has not provided. The last thing is parse command line. This one basically is called by the getRandVal, and this is what actually calls all the parsing in the A command line ops. And this returns a 0 if it is unsuccessful. Now let us look at some coding examples. First coding example is something which is like, as I mentioned earlier, about ISA stuff, right? Like used in CPU. So there's a small enum for an opcode which I created, add, sub, and mul. And then I've written some constraints over that. Like, okay, if the opcode is add, return order should be 3, and if add is sub, then return order is. Now let's focus on the pre-randomized function. In the pre-randomized function, what I'm essentially doing is I'm trying to figure out if the opcode has been overridden from the command. If not, the packet will basically kick in with default randomization and constraints, and at how many times you call the packet, it will create that state space. Now, in this example, in the first scenario, I'm giving plus opcode equal to add 80 and sub 20, which means I don't want the mul opcode at all. And I want, if I generate 10 packets, about approximately 8 packets need to be generated with the opcode of add, and about 2 of them with the opcode of sub. Now let's look at the second instance, operand equal to 32HFF, which I spoke about. This basically will give you the hexadecimal support is where what is kicking in here. Now, if you look at it over here, operand, the bottom 3 bits have to be 0. And we have specified the value in accordance with those constraints, so it should solve properly. Now, in the last example, if given operand equal to 32H000 to all the way to F, now there's a constraint which says that opcode equal to mul, then the operand cannot be done. This is where it kind of gets a bit tricky, because the constraint solver will fail if a mul opcode is selected and one of the values happens to be, which gets randomized in the pre-randomized step, happens to be not in the, with the bottom 3 bits not equal to 0. So this is something you need to be aware of, and every user needs to be aware of, that it has some limitations in this context. So I'm trying to use most of the constraints which are written by calling it in the pre-randomize and turning off the rand mode, but still letting the constraint to be solved. But in these scenarios, you might want to consider even turning off the constraint mode off for a particular constraint line. Coding example 2, this exemplifies the instance-based support which is provided by the advanced command line processor. If you look here, there's a sequence class and there are 2 instances of the sequence class. And I want to basically have the first sequence to have only delay of 0 or 1 cycle delays. The second sequence will see a range of delays. And basically by doing the UVM set config string and also providing the full path while calling the actual get ran val. This is where some of the extra optional knobs come really handy. If you want to use the UVM set config string, you need to provide a path so that the code recognizes and it will basically process it using the set config string instead of passing it as a plus arc. The third coding example, it's a very minor thing, but basically you can directly invoke this in that to DV connection. Just watch out for any port bit mismatch warnings. So you might want to, run it to a wire and then connect it. So that's the only drawback, but otherwise you can directly use it while hooking up your DUT. And this basically forms for a good configurable DUT, right? Sometimes you want certain signals to be directly controlled by the user from the command. So these are some of the coding examples which basically show the powerfulness of this code and how it can be used in various scenarios. So what are some of the benefits of my code? The benefits of this code is basically to avoid code redundancy, which you can see why, that everything is in those 2 classes. And for everyone else in any test bench, it's just plug and play. Just call the get run val and you'll get everything done. There's a central framework, as I mentioned before, for code optimization. So say, take the example of STD randomize. If there's some performance improvement there, I just need to change it in one place and it will just trickle down to the entire test bench or the entire DV flow. It's pretty scalable and portable. You can just take the snippet of code in my paper and basically try to create a class out of it and use it in your existing framework. You don't have to really touch any code to support it. If you want to start using it, you can start using it. Now you can, your ability to rerun and create multiple state space without having to recompile has shot up. You're essentially able to create randomization and distribution without having to recompile, which is a huge advantage in my opinion. You can also add this to existing RAL setups for randomization of the register setting. You can basically add it anywhere in your system-made log code. Some of the drawbacks. Let's discuss some of those. It's not a replacement of traditional randomization or constraints and never intended it to be. It just augments or enhances the existing constraints. Unidirectional amplification failure is possible, as I mentioned, so you need to be super careful. You need to turn off the relevant constraint modes if the user wants to override default constraints or default field values. Everything is string-based searches. So in larger databases, though I don't have any data to back this either way, it can start affecting performance, or something to watch out for, right? Next slide, future enhancement. So future enhancement, the goal is basically collect all metrics on each call and dump the database, and then post simulation, processing and visualization of database to ensure quality DV code. And basically we can have a feedback loop of the stimulus without having to write or dump coverage. So you'll have a good understanding of your traffic shaping without having to look at it. The entire code today, as it is made available part of the appendix of the paper, but at some point might need to come up with a better way to present all these future enhancements to the larger audience. These are the references, nothing fancy, just this is the Verilog LRM and the UVM class reference library. These are the documentations which I refer to. Time for some questions. Thank you.
Yes, thank you very much. And so one question I had as I was watching the presentation, how easy is it to document the command line options that you're making available? It seems like that could get out of hand pretty quickly.
Right. So when you say document is, yeah, so one of the optional fields is a description string which users can attach while calling the getRand val, which gets stored in the database. And one of the things which I've started doing actually since the time I wrote the paper and stuff is to kind of start printing those. So I can basically in the report phase or after a test, I can dump as to what was each option provided finally, which was picked, and also what is the description given by the user. And the other thing, in some environments, people have like a pre-run check using Verismo, some test bed lint or something. You can piggyback on that and basically extract this line and try to get like the description for each knob. So you kind of know what all is present in the entire test bench.
Okay, and a follow up to that. So it sounds like you can, at least during your report phase, dump what the command line options were used. But what about the user who might be coming into this? How does that user, have you given any thought to how will the user know which command line switches you've even made available?
Yeah, which is why I like the idea. So I've gone back and forth and I like the idea of piggybacking it on some kind of test bench lint or sub which runs before the compile or runs as people tend to sometimes run a lint to kind of check their code. So what I'm trying to do right now is trying to piggyback on that flow to get, okay, these are all the options which are available and I can parse it and make it available so that then people know what is there before even going into compile.
Okay, thank you.
Yeah.
And there's a question from Horace Chan. The command line is useful, but why use multiple plus arguments? Why not just pass the whole string into a single plus argument, then parse it?
I'm quite not sure. I don't know if probably the presentation was confusing or something. So it is a single plus argument, right? Like so for example, if there is a particular field, right? Say we want to control the delay, it is a plus delay equal to and multiple buckets, like n number of buckets separated by comma. So there is not multiple plus arguments. So
okay, let me let's see, Horace. Maybe you can come on. I think what you're also asking is not just the multiple arguments for one string, but the fact that he's putting multiple strings on the command line. Is that what the question is?
Can Horace speak up so that I can probably.
Yeah.
Horace, you're muted.
Oh, sorry. Yeah. So why don't we just use like one argument and then you pass in the whole string into it with like all the other arguments that you parse it that one argument.
And so Horace said that'd be a pretty big argument with some of the examples he showed, wouldn't it?
It's a string. Like it will be the same amount of characters, whether it's one string or multiple arguments, but it'll be a lot easier to deal with because you just save the argument.
Unix usually has a lower length limit for a single argument than for the length of the entire command line.
Oh, interesting.
Okay. Right. Daniel, thank you for coming in there.
That's one thing. And also, in a lot of the test bench infrastructure which people create, these command line arguments can be anywhere in the hierarchy. Some could be embedded right into the test definition. Some could be given into a common file. some could be provided right when you're running the test on the command line. So you kind of need to split it, right? Like it depends on the use case. So.
Yeah, and I'm only going to take one more question. I'm sorry, Armin,
Sure.
we're not going to have time, but please, maybe we can get Siddharth to answer your question in the chat window anyhow. But Alan Trottier asked, is the code available online, GitHub, or only via the paper appendix?
Right now, it's only via paper. That's what I spoke about in my future enhancements, that I'm trying to make it available via GitHub or something so that people can download it. Right now, the entire code is available in the appendix. I had, obviously I had to change the names and stuff from the company name. So, but I've done that, and I think if you copy paste it, it should execute. There might be one or two syntax error while copy pasting, but it should be possible. And also, just to quickly answer Armin's, like,
Okay.
It is like, possible to have all on a file. Yes, it completely depends on what kind of infrastructure we are using on top of the vanilla VCS or Cadence or, Mentor compilation stuff. So I think, it totally depends on that. So you can have everything in one file and just modify it there. And that's the thing, you don't have to always have these arguments to run your default test case, right? So it is only an optional add-on.
Okay, Siddharth, well, thank you very much. Good paper, good presentation. I will remind everybody that the voting for a best paper and for all of the scoring will end not too long after this session. So please get out there and do your voting. In the meantime, is Haoxiang, who has he joined us perhaps under a name that we don't recognize? Okay, so what we're going to... Yes.
I'm Haoxiang's co-worker. My name is Wang, the co-author.
Oh, okay. All right. Well, unfortunately, I only have a bio for Haoxiang, but let me read that. We will do the video, but at least now we know we have someone here, a co-author who can answer questions. Is that all right?
Yes.
Okay. All right. So yeah, let me introduce Haoxiang, who of Meta, who is the co-author with it looks like a tool Wang, and Haoxiang is currently an ASIC design verification engineer at Meta. Haoxiang has 8 years of ASIC DV experience, ranging from video encoder decoder, machine learning inference, computer vision processor, network on chip, as well as network routing chips. Haoxiang's DV ownership ranges from subsystem to blocks, as well as common DV flows. Haoxiang's technical skill sets include system like UVM, System C, formal, emulation, and various scripting language. And so we will now watch Haoxiang's presentation entitled Fnob, Command Line Dynamic Random Generator.
Hi, my name is Haoxiang, and I'm from Meta Infra ASIC team. Today, I'll be introducing a powerful constraint random tool, which is called Fnob. So talking about constraint random, we do every day in our DV work. What is a pain point? So in constraint random, we have so many different variations to do. For example, we need different values of the same random type, or different random types, or even different combination of a value and types within the test on the fly. Or maybe we just need a different combination of everything. As with so many different requirements for the constraint random, any easier way to do it. So let's take a look at the current solution we have using constraint syntax. There are many different ways to write constraint random tests, but here we present a most popular way to do that. So say, for example, we have a 12-bit variable to randomize, and we have 8 different tests, each one with a different requirement on that variable. The conventional way we do with the constraint syntax is to first write 8 different constraint blocks, each one corresponding to each test. Then we write 8 different system Verilog tests, each one enable or disable corresponding constraint blocks. And because all the system Verilog coding, including constraint blocks and tests, are inline coding, each modification or test we add, a recompile is needed. This may sound fine for one variable, but what if we have a full-blown test bench with hundreds of variables and thousands of tests to write? You see the pain point here. We have tons of code to write and a lot of huge turnaround time due to the recompile. So how does the Fnob helps here? With Fnob, what doing things, writing the constraint random tests will become much easier in the previous case. So here we have the same example on the same variable and the same list of tests to write. But instead of writing 8 different constraint blocks and the different tests, all we need to do is to write 8 different command line options. Each option defines the certain variable to override and its overriding random type as well as the value and probability sets, which we would introduce in details. And the beauty of that is all the command line variables applied in the simulation phase, which means no recompile is needed. So you see the benefit here. We eliminate huge amount of coding and we eliminate the recompile time. So looking at here, you must be wondering, what is Fnob? Fnob is called a dynamic random generator. It provides user both inline and command line override for both random type as well as random values. And it also offers, because of that, it offers a user a much simpler solution for writing constraint random tests, and to be surprised, it has a faster simulation performance time compared to the constraint syntax, which we will introduce later. Besides that, Fnob is a end-to-end solution. It also provides the built-in coverage to give users early pick on the coverage at the stimulus side. And it also offers mixed random, basically means you can mix different types and values in the same one-line definition, which makes the coding so much more efficient. Beyond that, we anticipate that if not, we cannot foresee all different types of a customized random in the world. So Fnob is architected in a very developer-friendly way so that it makes the user and the developer very easy to add new random types to Fnob and make it even more scalable. So how to use an Fnob? Using Fnob comes with four simple steps. And those steps are the same for any type of random type when you are using Fnob. So step one, first, we have a declaration. Declaration is the same as declare any other class variables. You have a class type, which is Fnob, and you have your handle, which is per user definition. After that, you need to instantiate the Fnob. To instantiate the Fnob, you need to provide 3 different types of variables. First one is a type of string, which is Fnob name. That name is user defined, but when you want to override that, the overriding name should be the same as what you defined here. This name will be the one used to register to the factory. Second parameter is Fnob type. This one is a predefined enum type, which defines what type of random you want to add, you want your Fnob to behave. The supported random types will be introduced in the later slides. Third one is Fnob parameter. So this parameter is dependent on the type of the Fnob you are defining. It can be only value, which means, for example, if it's a constant or it's a uniform random, it only needs values. But it can also be both value as well as probabilities. For example, in the case we have on the right side here, if you have a distribution type of a random, what you do, what you need to provide are two type of info. So value range as well as a corresponding probability. And we provided a one-to-one mapping correspondence between defining that in the Fnob in one line compared to defining that in the constraint blocks. Third step, once you declare that and instantiate your Fnob, when you want to use it and get a random value out of it, there is one simple API call you need to make, which is .gen function. This .gen applies to all Fnob types. So regardless of Fnob, a different type of Fnob you are defining, when you need a random value out of it, all you need to do is to call the .gen, and this will return the random value to you, which follows your defined random type and parameters. The default returned value type is 64 bits, but it can be customized because Fnob itself is a parameterized class. So you can put that to be integer or 32 bits or any other things based on your need. Finally, override. So override is the power of Fnob, which eliminates tons of code and as well as providing the benefit for no recompile. And there are two different ways to do that, which we will cover that in the later slides. But both ways are using the UVM config.db strategy. So talking about override, we support both inline and command line override. Both overrides are UVM config.db based, but there are two major differences in that. Inline override require as its inline system Verilog coding require the recompile, while the command line override directly applied to the simulation phase, which means no recompile is needed. This will play a big difference when you have a top level test bench, which takes longer time to compile, and this benefit will provide reduce that turnaround time dramatically. Another difference is inline override. You can define that anywhere in your test bench in the run phase, anytime you want. Basically, it supports multiple override per test. While command line override can only specify once, the last one wins if you specify multiple, and it only applied once per test at the very beginning of the new phase. So if you want one test, one variable to behave as different type of random at different stage of the same test, then inline override will use your pick for that, and command line override cannot do. So there's a pros and cons in both override, but both overrides offers strong implementation on the to make user writing constraint random tests much easier. And both overrides follows the same string for defining the type as well as the value. So the first variable, besides defining the path and all the UVM config.db required variables, are the name of the Fnob you want to override. Later on, the string you have, there's a type of the Fnob you want to override, as well as the required parameters you need, and the same variables will be applied to the COI as well. So let's take a look. Let's take a quick peek on the type of randoms we supported right now. So right now we're supporting total 10 different random types. That covers most most frequent usage we see in the day-to-day basis. So those cases include constant, uniform, distribution, equivalent to dist, in list, equivalent to inside, pattern, logarithmic distribution, C uniform, which is equivalent to rand C. And this is not the end of the story. We expect more different random types to be added to the Fnob by developers. And we created a very flexible architecture for that, which we will cover in the later slides. As we mentioned before, Fnob is built not just as a random value generator. It's also an end-to-end solution for random stimulus. One part of that is Fnob coverage. So for each variable, random variable you created, it will be good to have a pick on whether your random value how good your random value stimulus are at the stimulus phase. Fnob coverage provides that when you are using the Fnob to generate the random value. And there are two different ways that's implemented. For the random types that had a fixed length of parameters, for example, like a uniform random, which you only need a minimum and a maximum, we provide a basic built-in cover group per each Fnob variable, which covers the minimum, maximum, and the median value. For the Fnob types that has a variable length of parameters, say for example, you define a pattern, and you want to see whether you covered all the patterns defined in the Fnob, but that pattern can be different. It can be different sizes. So with that, we created to deal with that in the variable length way. We created a way that is basically an array of cover groups, so that for each when you have a list of parameters, for each value of that, it will create a cover group, and so that eventually you are going to see whether all values are getting covered for that variable, and that applies to other variables. Other variable lengths, Fnobs, like distribution, and so on and so forth. This is the basic built-in cover group we provided, and if user needs more advanced one, it can be overridden and replaced as well. So having said that, we now have the single type of random per variable available. It can do uniform random, distribution, pattern, many different type of things. But what if we want to mix them within the same test? And we want to mix them in the simplest way as we can, which means one line of code. Say, for example, if we want a variable to be 70% of time uniformly fast, 30% of the time constantly slow, like what we do in the delay and stall testing. What if you so how to do that in single line? That's where the Fnob multi comes into the picture. So in Fnob multi, the definition is different from the convention single Fnob. There are two different parameters you need to declare in the Fnob multi. First one is, as always, the name of Fnob. And the second parameter is actually a string of a string of Fnob definition separated by brackets. So the first Fnob defines the distribution of all the random candidates. Basically, here we have uniform fast, constantly slow, so we have two candidates. And the distribution we selected them followed this distribution, followed here. So this is the first control Fnob. The following Fnobs are all candidate Fnobs, which basically are the candidates of each random variables we expect. And one thing to note is here, the value for the control variables, the value for all the candidates starting from index 0 to 1 and to 2. So when you have the control here, the value should be limited to the number of candidates you have. So here we have 2 of them. So we have a 0 and a 1 and define it here and to be different type of distribution. So with Fnob multi, now what seems to be a complex task and require multiple lines of coding now can be done in single 1 line of a code. And this also will reduce further number of codes. Say if you want a different type of random combinations, without instead of coding up a separate code block, which is error prone and require recompile and all that, all you need to do is you can just override it on the COI using the same format specified it here. And it can be 1 line override as well. So all that reduce the coding as well as improve the test development time. So with that, let's summarize a little bit on the benefit we see by using Fnob in writing constraint random tests. So in the conventional way, when we use the constraint syntax, what we need to do are creating new constraint blocks and creating upper level test control, which, for example, in the top level tests, we need to enable or disable certain constraint blocks. And then we probably need command line switch to toggle different things. And because of the new coding we added, we need to recompile and then rerun to get what we need. So this involves tons of coding as well as tons of turnaround time. With Fnob, if we coded the Fnob override inline, what we need to do is just 1 line of inline override code, which reduces the amount of coding. And we skip all the upper level TB control and all that, and directly go to the recompile and rerun. This reduces the amount of coding time we have. And if the need we have can be achieved by Fnob command line, this will be further simplified. We don't need to write any more code in the system Verilog. What we only need to do is to write 1 line command line and then go straight to the rerun. So this saves both the number of coding as well as the turnaround time. Now we benchmarked the Fnob performance in the simulation time in 2 industry prevalent vendors. In both cases, with the same type of random and the same number of random calls, what we see is Fnob achieved a far better performance compared to constraint syntaxes. And we did a study on why is that? What leads to these huge differences? Here's what we find. Constraint syntax actually traverse the entire value space by the size of the data type. Say if you have and then apply the constraint on each data to see if that's a match. While Fnob only traverse limited value space by the predefined system functions, because Fnob in low-level implementation is based on the urandom and the urandom range, which is pure software implementation. With that, I think we think that due to the differences in the traverse space, bias the Fnob, the improvement in the simulation time. And when the number of calls are becoming huge and more and more, these differences will become significant, especially when it comes to performance or stress testing. So in both, and we see that behavior in both vendors. So at last, we want to briefly introduce the Fnob developer interface. So as we mentioned before, Fnob is not built as an exclusive tool, but to build as more like a developer-friendly, open-sourced way, so that Fnob can be scaled up with more customized random types from day-to-day works. That's why we created a separation of layers in the Fnob architecture. So part of the Fnob code are user level, basically infrastructure. So regardless of any type of random people are using or want to add, this part of infrastructure layer doesn't change. So this stays intact. The other half is called developer layer, which contains a file that developers needs to touch in order to add their separate random types. And we articulate those changes so that there's a clear flow for developer to add each type of random with predefined tasks. And we even provided a standalone test bench, which let user to test their random types before releasing to other users. This developer interface provides the scalability for any custom random types one user found in his projects to be applied to many other projects, so that improved the knowledge sharing within the whole team. So that's the end of our presentation, and we are open to questions and comments from all of you. So thank you very much for watching this.
Well, thank you, and let's see, and oops, hold on here. And Haoxiang has joined us, so he can also help to answer the questions. And so we'll ask Haoxiang, and I see Atul is turned on his video, maybe Haoxiang can as well. But we have had a few questions come up. First one from Paul Marriott. What if you have a lot of overrides? It could make for a very long line. Is there an alternate way of getting these in at runtime, perhaps from some kind of JSON file?
Thanks for the question. So for that, there are two different cases. So want to clarify is a lot of overrides can mean a lot of many overrides over the period of time, based or one single override with a very huge verbose input. So if it's the first time, we have no other way but to code it line by line inside the system Verilog code. If it's the second way, which means you have like one single override has a lot of info to pass. Right now, what we are passing is the horizontal way. Basically, we have all the info on horizontally. There like but like the we are working on we have a work in progress to also take the input vertically, basically to be more viewable. If say you have 10 different distribution possibilities to pass, but either way, we need to figure when we configure certain knob to behave in certain random patterns, we need to have a way to pass all the information to that knob, either vertically or horizontally. So right now we support horizontally. We are working in progress on the vertical like JSON or YAML format to make it more viewable.
Okay, thank you. And there's a kind of a two-part question from Lucas here. I'll get them both in there because I think they go together. What happens if we use both inline and CLI when running a test? Does it cause an error, or will the CLI override the inline? He continues. In the example of 70% uniform random, 30% random, is there a way for the user, maybe it's too different, the user to debug if he has inserted the correct values? How can we debug it?
COI will take a precedence at the beginning, basically because COI, we are not reinventing the wheel. We are taking advantage of a UVM config DB in that format. So COI will be active at the end of the new functions. So COI will override whatever you define or override at the beginning in the new function. But after that, if you have a further override, that further override will take effect with the simulation time passed. So to answer your question, at the beginning, COI overrides. COI proceeds later inline take precedence.
Okay. Hey, in the interest of time, we're only going to be able to take one more question, but I'll ask the authors to continue to communicate over the chat to answer some of these other questions. But Manoj asks the question, is Fnob open source for us to try it out?
We are working in progress on the open source process within our company, and we will publish the link once it's finalized.
Okay, well, thank you very much. And again, if you wouldn't mind looking in that chat window and answering a few of the questions we didn't have time for, I will remind everybody that there's very little time to do voting at the end of this session. So please get out there, cast your votes for these authors that spent a lot of time preparing this. So now let me introduce my good friend, Rich Edelman of Siemens EDA. Rich Edelman graduated from Washington University in St. Louis, Missouri, with a BS in computer science, a BS in electrical engineering, and a master's degree in computer science. Rich has worked at many EDA startups and now works for Siemens EDA based in Fremont, California. Rich is a verification technologist who helps verification teams develop successful debug techniques for UVM and class-based test benches. Rich's previous work includes register verification, system Verilog DPI development, and transaction recording interfaces for Questa. When not doing system Verilog, Rich can be found backpacking in Yosemite, or at least dreaming about it. We will now watch Rich's presentation entitled, "What Does the Sequence Say? Powering Productivity with Polymorphism," which kind of sounds like a book I would read to my grandchildren.
Hi, my name's Rich Edelman from Siemens EDA. Thank you for attending this talk today titled, "What Does the Sequence Say? Powering Productivity with Polymorphism." We're going to talk today about a UVM environment, and then we're going to extend it. We're going to do things to it, basically with polymorphism in the UVM. So our simple example is two interfaces. There's a driver, a transaction, and a sequence, and they're used twice in two different environments. What is the polymorphic UVM environment? Well, that is an easy way to replace sequences, replace transactions, replace drivers. So we'll replace them with better versions, and better is your definition as you find it. Well, better might mean get more by doing less. So that is some of the promise of object-oriented programming and polymorphism. But really, what is polymorphism? Well, in biology, there's two or more clearly different forms referred to as alternate. Oh, there's too many words. And then in programming languages, we can say, well, there's an organism or a species may have different forms. In programming, I guess programming is referring to biology. Anyhow, so there's a common subtype, and then there's more types that follow from it. So really, in the UVM, it's a better transaction, so improved transaction. It's bigger, it's smaller, it has different constraints. There's some other different business about a transaction or a sequence. A sequence is a program, a test program. It does a few things. Well, so now we have a different program. Maybe instead of a basic sequence, we have a self-checking sequence, or we have a sequence that has certain programming in it, like bandwidth requirements or latency, that implements video, UART, memory, other kinds of traffic. We could have a better driver, so a polymorphic driver, and this is a driver that handles interrupts where the base driver did not. So in our verification strategy, we're going to take our simple UVM test bench, which we saw in the first slide, and we're going to extend those sequences, transactions, drivers. So we're going to get new ones. And then finally, we'll reuse that strategy on a larger test bench with 6 interfaces. We'll do some virtual sequences. We'll talk about interrupt testing and some synchronized testing. So system Verilog UVM polymorphism. It's a simple idea, and it's just easy to say it out loud. It's a is-a relationship. So a racquetball is a ball, a basketball is a ball, a racquetball is a basketball. And anybody who's got a keen eye knows that one of these bullets is incorrect. That's a homework assignment. So we can figure out what the relationships are with the ISA. And so in System Verilog, we would say a class super transaction extends a transaction. So we could also say a super transaction is a transaction. So this is the better transaction. So let's jump right into some definitions in System Verilog that are a little silly, but it's a ball. So we have a ball that we're defining, and a ball has a function called getName, which returns its name. It's a virtual function. That'll be important later. It also has a print routine. The print routine is also virtual, and the print routine just calls the name function and prints it using $display. That's it. Then we're going to make a basketball. It's a better ball. So we have a polymorphic ball, a basketball. It's extending a ball. And it needs a new name function because it has a different name than a ball. So in this case, what we're going to do is we'll call super.getName. So that calls the base class getName, and then append or prepend basketball to it. So that's the new name. That's the new function for basketball. And then we have another one, a kids basketball extends basketball. So a kids basketball is a basketball. And of course, it also is a ball. And it needs a new name as well. So here we go, same thing, super.getName. We have a professional basketball, and same thing, getName. A racquetball extends a ball. Same thing, a new getName. Now we're going to use our little objects. So we declare them up here. And then we have an array of 5, and it's an array of ball objects. And then we're going to construct them. And then we're going to fill in that array. We're just going to fill them in. It doesn't matter. And then we have a for each that array. So we're doing a for each on an array of balls. And so it's essentially, ball.print, basketball.print. And so this any ball is an array of balls, but inside that array is actually all kinds of different balls. So this is the power of being able to call a print function of the object that's in the space, the object that's in the array, not the actual declared value of ball, because we wouldn't want ball print to be called each time. We would want pro basketball print to be called. So, and then this is really the same thing. So we have an object called ball. It's of type ball. We assign the racquetball pointer to it. So now it's pointing at an object of type racquetball. And then we're going to call ball.print. That prints the racquetball version of print. All right, getting back to our environment now that we're trying to use to verify our hardware. We have a little bus here. It's not so important in this talk, but it has a read-write bit. It had some address bits, a byte of data and a byte of write data, a byte of read data, an ID, a ready valid signaling, and 2 interrupt signals. Okay, so we start out with our transaction. This is the thing that we're going to pass around, that we're going to randomize. We're going to maybe extend polymorphically. So it has a read, write, and address data. It has a low address and a high address. That's used in this constraint to control legal range, the legal range of the address when we randomize. And it has an ID. And then it has that legal range constraint and a maximum length. So you get a legal range, and you get from 1 to 15 bytes. And our transaction has a pretty print, convert to string. It's really just making a pretty string that you can use to identify your transaction. It prints out the address, the data, and type name with the ID. Then we define a do record. That helps with transaction recording. Easy to put up a transaction now. And then we have a compare routine. And this compare routine is easily written. It's looking at the attributes that are important. If there's a mismatch, it returns 0. If we get all the way through the checks, then we return 1 because it matched. And then we have a sequence. So we're going to have a bunch of transactions. that we send through, and this sequence is going to do it. This is our basic sequence, has a transaction handle, and it has a field called maximum transactions, which is going to control this loop in the body. When we construct it, we're going to set the maximum transactions to 100. Then we're going to have this body loop, and we're going to create a name. We're going to construct a transaction object with the factory, and we're going to do start item, finish item. And in the middle of that, of course, we're going to randomize. So this is just regular old UVM. So this sequence is going to send transactions, probably 100 of them. So now we're going to make a better transaction. This one only has odd addresses. We're going to take our transaction, extend it, so it's a polymorphic transaction, and add a new constraint. So we have a new constraint called odd address, and it just says, well, add bit 0 should be 1. And so this will get applied when we call randomize on our object. We're going to have a different extended transaction, the big transaction. And so we're going to replace an existing constraint. So there's an existing constraint in the base class. We're going to change it. So we change the max length constraint to make transactions that are bigger. We're also going to add a fancier transaction, a double. So this transaction has an extra class member variable called address2, the second address, and it has a legal range constraint for it and a value constraint for it, meaning we don't want to have the two addresses match. We're going to redefine convert to string to pretty print the second address, and that's it. So now we've got a few transactions that are better. Now we're going to get a sequence that's better, and this sequence is called the checker sequence, or self-checking. So it takes our basic sequence and extends it, and it's going to redefine the body. And we have an array here of write data. This is the data that we've written. It's the same maximum transactions loop, and we're going to do call the constructor start item, finish item for a write. And then we're going to save the data that we wrote. So that was whatever random data we wrote. And then we're going to force a read, and we're going to do a start item, finish item for the read. Now, when that returns, we're going to check the write data against the data that we read. If there was a mismatch, we'll issue a message. So now we have a better sequence. We can feed that right in without doing really much work at all. And we have a self-checking sequence. So we talked about constructing those transactions and sequences from the factory. Well, that's a great idea, because in the factory, you can override things. So the UVM factory replaces one thing with one thing. So you can say, I would like every time I ask for a basic sequence, instead, I would like to have a checker sequence come through. So that's the way that you would use the UVM factory. So that's great. So now every basic sequence can be replaced with a checker sequence. Every transaction can be replaced with an odd transaction. And then every transaction can be replaced with a big transaction. Oops, wait a minute. We actually want to have our sequence pick one of our three. We have three better transactions, actually maybe even one of our four. So that's not going to work. The factory won't work. We can only replace one thing at a time. So how about instead of a factory, we use a picker? That's a technical term, picker. So this is the code for the picker. This is the whole code. This is it. And I'll just say ahead of time, it is much smaller than the UVM factory code, which is around about 1,500, 1,600, 1,900 lines, depending on which version you use. So this is the picker. The picker has a queue of types, and it has a queue of numbers, just to keep track of how many each one we have, where we are on the count. Okay, so if you want to use the picker, you call add, and you just push that type onto the types queue. If you want to get an object, like a factory, you want to allocate, create, construct an object, you call get. That's it. So the get routine has a transaction handle that's going to get returned, and it generates a random number, and that random number is used to index into the queue. So now I'm indexing into that queue, getting a handle, getting a value out of there, and calling create object. Create object is a function that the factory actually does use. So this is built into the UVM. So I'm calling a create object on that type, and I'm going to get an object handle. I'm going to make a name, a special name using that number queue, and set the name, and then do the cast and return the value. So that cast is just a fancy way to have a TR handle that's really a TR instead of a UVM object. That's it. That's the whole code for the picker. Well, how to use the picker? You just call transaction picker : add, and then you say, I want to put my transaction in there. And then there's some syntax over here, get type. And then I want to put my odd address transaction in there, my big transaction, my double transaction. So now they're all in using the add routine. And then any place where we had been calling the factory, so any place where we're doing transaction type ID create, we're going to replace that with transaction picker : get. That's it. That's all we have to change in our code. So our sequence is going to call transaction picker : get. Now, anytime we call that, we're going to get one of 4 different transaction types randomly. So that's great productivity because now you get all these different traffic patterns. All right. So what about some other kinds of transactions? Well, the interrupt transaction is very simple. This is it. It has a count, it has an event. The count just is useful to keep track of the number of these that have happened. If you had a real example, you might have some other things in your interrupt transaction that you wanted to pass back maybe from the interrupt. And we just have a pretty printer. Okay, so we're going to have an interrupt sequence, and it's pretty simple as well. It extends the basic sequence, but inside it's a little different than most sequences. It has a handle to one of those interrupt transactions that we just defined, and it is a for loop, forever loop, and it is going to allocate one of those interrupt transactions, and then it's going to do a start item, finish item on it. And really, this is request to send and then go. And then it's going to wait, and it's going to hang here until the driver signals using that event that's in there, that flag. So what's going to happen is this interrupt sequence will wait until there's an interrupt, and then it will continue processing. So you could put some other processing after this, and it'll reset after that. So this interrupt sequence will wait until it gets an interrupt, and then you can put processing in here. So what happens in the driver to make this magic happen? So the driver, this is an extended class. This is a polymorphic driver. We're going to replace that driver in the environment, and it's going to do the usual things: get next item and item done. And in here, there's if then else ladder here. So we're using cast to figure out what kind of transactions coming through. Because in a polymorphic world, there could be many different types of transactions coming through here. And we're going to use this cast. It will either succeed or fail, 0 or 1. If the assignment is allowed, meaning this is an interrupt transaction, then we'll take this leg of the if then else. So now we are, if this is an interrupt, okay, that means we're going to do our interrupt service routine. Come back to that in a second. If it's not an interrupt, then, well, is it an out of order transaction? So we're going to cast this to the out of order handle. And if that works, then that means it's an out of order transaction. We'll process it, and so forth and so on until there's no special handling. It's just a normal transaction. And so the normal transaction is handled by a routine called process sequence item, and the transaction gets sent out onto the bus or whatever else is going to happen. So getting back to our interrupt service routine. So in this case, the driver does a get next item a fork join none, that spins a thread. So now there's a thread running, and it does item done, and the sequence can continue. But what that interrupt sequence is going to do is it's going to be waiting, and this interrupt service routine task is going to be getting waiting for the interrupt on the actual bus, and then doing a little counting, and then signaling that event. That event will release the sequence. The sequence can continue with the processing. So this is a polymorphic driver. We just replaced the driver, and now it can handle interrupts. What's a fire and forget sequence? They're the easiest. Maybe it's background traffic, checkers, monitors, some other long-running process. You start it and you forget it. So the starter might just be, oh, I have a sequence somewhere, maybe that's going to start it. It does a fork join none and starts that sequence. Fire and forget. Video sequence really is just sending bytes, but it's sending special kinds of bytes, maybe a lot of bytes. So we're going to turn off the constraint mode for max length. We're going to set the constraint mode to 0, and we're going to do a start item, randomize that thing with the data size equal to some big number probably. Do a lot of bytes, set it to write, and then do the finish item, and then the video sequence will go out there. What's a virtual sequence? Well, virtual sequence really is nothing special, but it's very useful. It's just sequences that start other sequences. So for instance, you could have a sequence, a virtual sequence, start these other two sequences, and maybe poke into those sequences. We'll see that in a second. You could have a different virtual sequence that starts two sequences and then gives the handles of those sequences to each other. So now they have handles to their cohorts in crime, and they can work together on something. So in our larger system, we're going to have 6 interfaces, 6 sequences, and we're going to synchronize things. So we want everything to be ready, and then we're going to read. And we want everything to be ready, and then we're going to write. That's the way this test is going to work. So all of these sequences are going to have those random transactions, big ones, little ones, and are going to synchronize. So we just talked about, so what does the controller do? It waits for everybody to be ready, and then it signals go. What do the controlled sequences do? They set themselves to be ready, they wait for go, and then once they get go, they do whatever they're going to do, reads or writes. All right, so those controlled sequences down low are synced. We're calling them synced here, and they have a few bits, that's it, nothing fancy. And then they're just exactly like you might expect. They have that maximum loop, and they're using the picker here. So I'm doing the picker transaction, and I'm waiting here on proceed to write. So I will wait until I get my event, proceed to write. I'll signal the controller I'm waiting by setting this to be 1. Then once I get the go ahead, I'm going to do start item and then finish item. In between, I do my randomize, and then I get my write data, just like the checker sequence, and so forth. And then I can do a check. This is the read over here. All right, so what does the synchronizer do? The synchronizer, upper level, is gonna have a whole bunch of handles. It's gonna do a wait. So everybody has to be at 1. Everybody has to be ready. And then it's gonna do proceed to write. So it's gonna do the event. So it does everything, and then it does the same thing for the read side. So it's pretty easy, forever begin end. It's just going to sit there synchronizing everybody. So the upper level, the body constructs those sequences. So this is the virtual sequence constructing its lower level guys, starting the synchronizer, and then it starts those sequences. That's it. So the virtual sequence is just responsible for the goings-ons, the sequences that are on those 6 interfaces. All right, so we took a quick tour through a simple test bench, but with just a small amount of code, we expanded to 4 different transaction types, a couple different sequence types, and can generate lots of traffic. We talked about interrupt handling and a simple way to handle interrupts. We talked about synchronized sequences and how to control them using a virtual sequence. And in the end, our goal really was to get lots of activity in our test bench. And you can see here, these are the transactions in the wave window, the different objects. So we had a lot of different kinds of objects going through. They take a variety of different kinds of times. And these are all synchronized so that they do their reads and their writes in order for this larger 6 interface example. Thank you very much. And now we'll take some questions.
Okay, that's great. Thank you, Rich. And so as a matter of fact, let me turn my video back on too. But there a rather long question in the chat window. Let me narrow it down a little. It says, hi, Rich, say I have a transaction type that could represent an action that will be passed to an agent that will elaborate that action and generate UVM sequences on various driver based on the action definition. Could this transaction picker implement the PSS action graph and pick one of the available actions at the current point of the graph? Alternatively, is there a better tool for the PSS test to UVM connection? From Jonathan David.
That's a good question. I don't know if there's a better tool, but sure. So the picker just picks something randomly. So if there's a graph underneath, yeah, you could use it that way. We were just using random range, I think.
Okay. Now, have you done the question for me? Have you done any benchmarking on your picker versus the factory creation? I mean, the lines of code, it kind of stands to reason that it'd be faster, but I'm wondering if you've done any benchmarking there.
No, didn't do any benchmarking. Just a small test case. Yeah.
Mm-hmm.
Yeah.
Pretty cool presentation. I'll tell you, I learned a lot of new things there. I'm going to have to implement myself. Does anybody else have a question before we end this session? And I do want to remind you can still post your question. I do want to remind everyone that we have very little time to do rating on these presentations. All these authors have spent time, and so they would appreciate you going out there and rating what they've done there for you.
All right. Thank you all very much.
All right. And Paul just says interesting session. All right, guys. And so let's go ahead and close this, but please do go out there. Please do rate the presentations from these authors. And we thank you all for attending this session.